Hello and welcome to G Fun Facts Online. Today, we're stepping back in time, not just to look at ancient ruins, but to uncover the secret of how they're still standing. Think about the Pantheon in Rome. Its massive, unreinforced concrete dome has stood, nearly immaculate, for almost 2,000 years. Or the Roman aqueducts, some of which still carry water today. Now compare that to a modern concrete bridge or building. Many start showing cracks and decay within just 50 years. How did the Romans build structures that have defied earthquakes, the relentless sea, and the sheer weight of millennia? For centuries, it was a lost art, a forgotten secret. But today, modern science is finally cracking the code of Rome's immortal concrete. So join us as we explore one of history's most remarkable innovations. Now, the Romans weren't the first to mix up a batch of cement. People in Syria and Jordan were using basic forms of concrete as far back as 6500 BC, and the Egyptians used mortars to build the pyramids. But it was the Romans, around the 2nd century BC, who revolutionized it. They called it opus caementicium, or cement work. And it wasn't just a binder, it was a primary building material. Their breakthrough came from a happy geological accident. Near the city of Pozzuoli, on the Bay of Naples, they found a special volcanic ash. They named it pozzolana. The Romans discovered that when you mix this ash with lime and water, you get a mortar that is incredibly strong and, most importantly, can harden underwater. This was a game changer. Suddenly, they could build robust piers, harbors, and breakwaters, which were crucial for their navy and their trade empire. The architect Vitruvius even wrote down the recipe around 25 BC, 1 part lime to 3 parts pozzolana for buildings, and a stronger 1 to 2 mix for underwater work. This recipe, combined with aggregates like rock or broken tiles, became the backbone of the Roman Empire's architectural might. But when the empire fell in the 5th century AD, the complex supply chains for high-quality pozzolana collapsed, and the secret of its large-scale production was largely lost for over 1,000 years. So what was in this miracle recipe? For a long time we knew the basics: lime, water, and that special volcanic ash, pozzolana, which is rich in silica and alumina. When mixed with lime, it kicks off something called a pozzolanic reaction, forming an incredibly stable and durable binding agent. But recently, scientists noticed something odd. Sprinkled throughout Roman concrete are these tiny, white, millimeter-sized chunks. For decades, experts dismissed them as evidence of sloppy mixing, a flaw in an otherwise perfect material. But a team from MIT and Harvard proposed a radical new theory. What if these weren't a mistake? What if they were the secret? They theorized that the Romans weren't just mixing lime, but quicklime. Instead of first slaking the lime by adding water to make a paste, they likely tossed the quicklime in directly with the pozzolana and water. This triggers a powerful exothermic reaction, a process now called hot mixing. The mixture would have heated to extreme temperatures, and those little white chunks are leftover bits of lime, which they called lime clasts. This hot process had 2 huge advantages. First, the high temperatures create unique chemical compounds that make the concrete stronger. Second, the heat drastically speeds up the curing and setting time, meaning the Romans could build much faster. But the most incredible function of these lime clasts was yet to be revealed. This is where it gets truly mind-blowing. Roman concrete can heal itself. Imagine a tiny crack starting to form in a 2,000-year-old wall. That crack naturally finds its way to one of those brittle lime clasts we just talked about. Then, the next time it rains, water seeps into the crack. This water reacts with the highly reactive calcium in the lime clast, creating a calcium-rich solution that quickly recrystallizes into calcium carbonate, essentially calcite. This new material fills the crack, sealing it shut and even strengthening the repaired area. It's like the building has its own immune system, automatically repairing damage before it can become a major problem. To prove this, researchers made their own hot mixed concrete, cracked it, and ran water through it. Within just 2 weeks, the cracks had completely healed, and water could no longer pass through. Control samples made the modern way showed no healing at all. This self-healing ability is a huge reason why Roman structures have survived so well, especially in earthquake-prone areas like Italy, where constant minor cracking is a fact of life. If the self-healing wasn't amazing enough, consider what happens when Roman concrete meets the ocean. Seawater is the ultimate enemy of modern steel-reinforced concrete, corroding the steel and causing the structure to crumble in a few decades. But Roman harbor walls and piers have been battered by waves for 2 millennia, and in many cases, they've actually gotten stronger over time. How? When seawater works its way into the concrete, it reacts with the pozzolana and lime. This chemical reaction grows rare, interlocking plate-like crystals of minerals called aluminous tabermarite and philipsite. These crystals fill in the cracks and pores of the concrete, reinforcing the entire structure from the inside out. The very thing that destroys our modern marine structures was a catalyst for strength in Roman engineering. The concrete was essentially a living stone, in a constant chemical exchange with the sea that made it more and more durable. This incredible material, opus caementicium, didn't just make strong buildings, it completely changed architecture. It freed Roman designers from the simple post and beam construction of the past. With concrete, they could build massive arches, vaults, and domes, creating vast open interior spaces that had never been seen before. The Pantheon's dome, 142 feet across, and still the world's largest unreinforced concrete dome, is the ultimate example. They even engineered it with lighter aggregates like pumice at the top to reduce the weight. Concrete allowed for the scale of the Colosseum and the efficiency of the aqueducts. But now, this lost art is being rediscovered, and it could be a key to our future. The production of modern Portland cement is responsible for about 8% of global CO2 emissions because it requires heating limestone to around 1,450 degrees Celsius. Roman concrete was made at much lower temperatures, around 900 degrees Celsius, giving it a much smaller carbon footprint. Combine that with its incredible longevity and self-healing properties, and you have a recipe for truly sustainable infrastructure. Researchers are now working to commercialize modern versions of this ancient recipe, potentially using industrial waste products like fly ash to mimic the volcanic pozzolana. So the secrets to Roman concrete's immortality weren't just one thing. It was a perfect storm of innovation, the right material in pozzolanic ash, a revolutionary hot mixing technique, and an ingenious design that resulted in a material that could heal itself and even get stronger when faced with its greatest enemy. For centuries, these secrets were locked away in crumbling ruins. But by looking back and understanding the incredible ingenuity of ancient engineers, we are now paving the way for a more sustainable, more durable, and more resilient future. The enduring legacy of Rome isn't just written in books, it's cast in stone, a testament to innovation that has, quite literally, stood the test of time. Thanks for listening to G Fun Facts Online.